Hello, my name is Taiki Iwao. I'm from Hiroshima University. In this presentation, I'll give a speech about my proposed system to forecast the real-time congestion through BLE beacons. This slide shows the outline of my presentation. In this presentation, it consists of below 6 parts. The first is the introduction, and then next is the preliminaries, the detail of proposed system, the engine of the parameter prediction, the evaluation of this system, and the last is the concluding of this presentation. First, I'll explain the abstract of proposed system. The main purpose of this system is to forecast the degree of congestion in a specific space. To forecast the degree, this system consists of two steps. First, detecting users' movement using BLE beacons. Second, to forecast the congestion, we estimate some parameters express it well. After using results of this, we can see how change the congestion in a space. Also, the outcome of prediction is notified to remote users through the internet, like congestion X after T time. And it's an important assuming for predictions in this system that users' arrival times should follow a probability distribution. I'll introduce the three related works. First, in the case of acquisition through BLE, a group at Kent University used BLE devices for acquiring the behavior of visitors at the big event. Next, in real-time congestion predictions, a group in Taiwan developed a highway monitoring system, which is not based on BLE beacon. Finally, in the case of trend-based analysis, Google uses statistical data and periodicity data for the congestion forecasting. In this system, we have planned to combine these ideas to forecast congestion. In this system, we assume that every user in the monitored space is assigned a specific role. Therefore, their movements can be represented by a specific probability distribution. Also, periodic factors in the input data can be removed by referring to appropriate statistical data, and the user's status changing from arrival to departure can be physically monitored. How can we express the congestion in a space? We consider a case of the way to inquire the congestion. Then, that can be represented with two options to inquire. One is to inquire how much congestion is it after X time. The other is when is the time next congestion reaches Y. We also consider in the case of how can we express the congestion in a space. There are two ways to express the degree of congestion, we think. One is to measure objectively and express it as a percentage. The other is to measure and express subjectively. In this system, we adopt the second idea because of technical difficulty of obtaining an objective congestion level. Alright, I'll explain the method of acquiring the user's movement data at first. In this system, we use some BLE beacons to detect a user getting into the specific area. Each beacon continues to send a short message, having the beacon's ID and token to identify the user in the space. Users in the target space receive that beacon's message, and then they send it to the cloud server through the internet with the time received. If user's disconnection flag is true and the same message is notified, that means that users getting out of the space in this system. Also, we can extract the user's arrival time and stay time from timestamp stored in the server. Next, I'll explain how does it forecast in this system. First of all, estimated parameter is obtained from server's stored data and online data through beacons. And then this system determines how shape the distribution is and identify the value at the specified time in the distribution. Finally, the congestion level is determined by how the value of identified most explains the classifier. First, we should consider two distributions of arrival and stay in estimating parameter. In general, arrival distribution is more important for prediction than that of stay. Thus, in this presentation, after this, we will focus only on the arrival times and assume that stay times are constant. Also, there are two specific methods for the parameter estimation. One is the maximum likelihood estimation. The other is the steepest descent method. Since we found the former exhibits a much better performance, we adapt the former in this system. The next, considering the actual environment. The input data is visible only before a certain time. In other words, samples would arrive after a specific time, such as certain time, are all hidden. We should consider the incompleteness of the input data during estimating. Therefore, to compensate this incomplete data, estimating on this system includes the following steps. First, preparing similar distribution patterns. Second, filling in the missing part with each pattern and estimating parameter over these filled patterns, and inactivating the pattern, generating outlier result. Finally, calculating weighted average of resulting parameters over all active patterns. With these steps, we can solve such an incompleteness in the input data. Third, the final. I'll explain what maximum likelihood estimation is. In assuming X is a set of samples according to a distribution F, maximum likelihood estimation in constant is a method to search and determine the best parameter sheet hat of the distribution from a sample set of X. Maximum likelihood estimation is a powerful method to determine the best parameter, but there are some cases it would be easy to solve by this method in a simple way. For example, normal mixture distribution, which consists of some normal distribution, is the actual case. If the argument of log likelihood function is it, the linear sum in the log function makes the analysis difficult because the sum is in the log function. Then, this problem can be solved by EM algorithm. EM algorithm, accurately called the expectation maximization algorithm, is an iterative method to find maximum likelihood parameters with repeating E and M steps. In considering the log likeliness of normal mixture distribution, the function Q defined at the above in equation is focused on the EM algorithm. EM algorithm repeats the E and M step to find the parameter lambda of maximizing Q and the parameter theta that is more likely maximize log P. With these steps and in equation, we can obtain a more likely parameter theta of log likeliness of normal mixture distribution. In the final section, I'll explain the performance of the proposed methods as a part of congestion forecasting system. The first experiment, we evaluated the validity of modeling the arrival time of users with a normal mixture distribution. In this experiment, we had acquired the trend of users' arrivals. There are 96 students at a specific class through connecting BLE beacon between 8 am and 9 am. These two graphs show the trend of users' arrivals for two specific days, where the horizontal axis is the elapsed time from 8 am and the vertical is the number of students arriving in the given minute. In these graphs, it compares the distribution of actual data and that of artificial data generated according to extracted parameters of the actual data. And seeing these two graphs, there are similar peaks in the distribution of actual arrival times, which could be well explained by the modeling with a normal mixture distribution, indicated by a dashed curve. The next experiment, we evaluated the impact of the number of samples in estimating with EM method and the relation between the similarity of parameters and the difficulty of estimating. In the left graph, it shows a relation between the number of samples and the estimating error of the EM method. Then, this graph indicates EM method needs over 100 samples because the decreasing of estimation error becomes small over near 100 samples. On the other hand, the right graph explains the relation between the similarity of parameters and the difficulty of estimating. We can assume the relation of the error and parameter from two perspectives. One is the case of focusing on the difference of two means. It was confirmed the error of the EM method becomes largest when its difference is around 0.4. The other is in terms of the variance. The error is getting larger by the smaller the difference between two variances. The last experiment, we evaluated the prediction accuracy for incomplete data and searched a better way to fix the incompleteness in the input data. In this experiment, we set 5 borders to represent the incompleteness in input data. The borders consist of each quarter of the gap between two means of two normal distribution inclusive. Also, consider the 3 heuristic data patterns. 1. There is no data to fill the masked point with. Second is a case of filling with a uniform distribution. Finally, the case that the data to fill with is a fixed normal distribution, not a part of the underlying distributions. This graph shows the result. In the pattern of filling with no data, the larger the range of masked, the larger the error is. In the other pattern of filling with a uniform distribution, if the range of masked is smaller than a specific point, such as T2, the error becomes very large. The reason of that is the added data becomes a noise to estimation, and it makes the error large, I assume. In the case of a normal distribution, it seems like the performance of estimating is better than the other filling patterns. This is because that the normal distribution to fill with is, in focusing on the shape, similar to the part of the original distribution even if there are some difference between these parameters. Also, to compare the performance, two cases of a mixture distribution with correct parameter or incorrect. It is of course that the more similar the parameter of the distribution to fill with to the actual of that, better result it appears. In addition to it, the number of samples to the filling data is also important to get a positive result. These results show that we should focus on the 2 points to fix the incompleteness with the distribution. One is a parameter, and the other is the number of samples to fill with. In this system, we propose a method to forecast the congestion level by the online data to determine the parameter, and the statistical data to determine the shape of the distribution. As a future work, we should enhance the forecasting engine, for example, searching better filling method or better use of online data, such as not only for estimating parameter, and evaluate the performance in actual environment. This is the last slide. Thank you for your listening.